Now this screencast is on gravitation, and it's tied to the section on circular motion. So the first thing that we'll start off with is the universal law of gravitation, which is something that you will have seen in physics 11. That the force of gravity on something is G m1 m2 over r squared. So the value G is the universal gravitational constant, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. This formula is to find the force of gravity between any two objects. So m is the mass of the one object, m2 is the mass of the second object, and r is the distance from center to center of the objects. Now that's a common mistake, so something you have to be aware of, and it's always from center to center. Whether it's something going in orbit or just two bodies, we want to go center to center. Remember also that this is force of gravity, only attracts, it never repels. Now when we do problems on circular motion, you'll find a lot of times you'll be given r, and r will be the radius of the path or radius of the orbit. And so if you're given that number, then that's all you need, is the radius of the orbit. However, you do have to be careful, because if we're talking about a satellite that is located, let's say 100 kilometers above the surface of the Earth, which you may be given, that won't be enough to figure out the radius of its orbit. So in this case, you'll have to add the radius of Earth to that number so that you have distance to the center, or the radius. Now if we look at the formula more closely, we have been studying force of gravity for a while now, and whether you've used this formula or not, we still are able to calculate force of gravity. But I'll show you how this formula can be changed to something you might be more familiar with. So if I take this, let's just say we're talking about the mass of a person, and this person is, let's just say, standing on Earth, then I can rearrange this. Sorry, I don't know what happened there. I can rearrange it so that I have the mass, so the mass of the person times G, mass of the planet, or let's say Earth in this case, over r squared. And now if I work this out, if I take 6.67 to the minus 11 times the mass of the Earth divided by the radius of the Earth squared, I get a number. And this number is 9.8 meters per second squared, which should look familiar to a formula that you've used before, where force of gravity is mass times g, the acceleration due to gravity. So what's happened is, to save us time from working out this formula over and over and over again, we take this section, work it out, and that works out to 9.8 meters per second squared. So we can find the force of gravity of something if we know the value due to acceleration. 9.8 is on the surface of the Earth. On the surface of the Moon, it'll be 1.6, and on other planets, it'll be something different. So it is possible to calculate force of gravity if you know the acceleration due to gravity. Okay, on weightlessness. We feel weight because we feel an upward force pushing against us, like a normal force. However, in a falling elevator, you would feel weightless for your final few seconds anyway. But as you fall outside, you do feel air friction, air hitting against you, and so that kind of helps a little bit. So you're almost weightless. But in a closed container that's falling, like an elevator or something like that, then you'd be floating around just like someone would in space. With satellites, they are in a steady orbit, but at the same time, they're also considered to be in free fall as well, which means weightless. However, this free fall of the satellite, it's counteracted by the fact that it has a speed that keeps it going in the circle, this orbital velocity, which will keep it going forward. Now, for the satellites, we can find orbital velocity by making an association. We say that it's moving in a circle, and so because it's moving in a circle, we can use centripetal force. But centripetal force is not a real force in itself. Something is causing it. In this case, what's causing it to go in a circle is a force of gravity. And so we say mv squared for the satellite, r, equals, and maybe I'll put an s subscript for satellite, equals g, mass of satellite, mass of our planet Earth, over r squared. And now I can cancel stuff out and say, okay, mass of satellite, and one of the r's. And just be careful for this unit, and this just becomes 1. One of the most common mistakes is algebra mistakes, especially with the r's. A lot of times instead of cancelling out, people get r cubes, or instead of r cubed, people cancel r's. So do be really careful with the algebra in this section. But anyway, if I go on and I solve for v, then v equals g times the mass, in our case mass of Earth, but it could be any planet, over r is the radius, distance of your object to the center, I should say. So this formula could be used for other planets if you know the mass and you know the distance to the center. But one thing I will ask is try not to just memorize this formula, even though you'll be using it a lot. It's much better if you remember all the steps. If for nothing else, when I mark your work, I can see what your understanding is, and I can see that you make this association here, and that you're able to plug things in and then solve for v. Whereas if you just use this bottom part here and you make a mistake, I don't have a lot of room to give you part marks because I don't see exactly what you're doing. So if we do an example here, so we're going to start with association again. It's in an orbit, so it's in the circle, so we centrifugal force. What's keeping the circle is force of gravity, and so I will use mv squared over r equals g m1 m2 over r squared. Maybe just to simplify, I'm going to say this is mass of satellite, and I'll say that's mass of Earth. Well, I can do some cancelling here. And okay, cancel out mass of satellite, cancel out one of the r's, this is 1. And so now I can solve. So v equals g, mass of Earth, over r. Now before I continue, I need a little bit more information. First, I need r. So if the satellite is 350 kilometers around above Earth, then the distance to the center, or the radius of its path, its r is going to be the radius of Earth, 6.38 times 10 to the 6 meters, plus the height above Earth, which is 3.5 times 10 to the 5 meters, and that gives us 6.73 times 10 to the 6 meters. And we'll also use our formula sheet to get the mass of the Earth. So then our velocity is going to be 6.67 times 10 to the negative 11 and times 5.98 times 10 to the 24 kilograms divided by 6.73 times 10 to the 6 meters. That's our distance. And so if we solve for v, it works out to about 7,698 meters per second. Or maybe something that's easier to imagine, 27,700 kilometers an hour. Wow, that's pretty fast. What it actually means is that this International Space Station does over 15 orbits around Earth in one single day. Our next section is on Kepler's laws. Now, Kepler's laws isn't technically in the curriculum, but it's a pretty important thing to learn about, especially because it makes solving a lot of these problems much quicker. And so, to get a detailed explanation of Kepler's laws, then I want you to look through the notes and make sure you read all the notes, especially this section, to look at the different laws. What I'm going to deal with is the equations that you get, or the equation that you get as a result of his third law, and that is the constant relationship that he found between radius and period for objects orbiting another object. So basically, what he found was the radius of an object's orbit cubed divided by the period of its orbit squared is equal to the radius of another object's orbit cubed divided by the period of another object's orbit squared, as long as the two objects are going around the same body. So, for example, if I wanted to look at a satellite and learn about it and use this equation, I could compare the satellite to the moon because they're both going around the Earth. If I wanted to look at a comet that is traveling around the sun, then I can compare that comet to Earth because they're both traveling around the sun. If a satellite is in a geosynchronous orbit around Earth, how high is it above Earth? So, this means the satellite's period is going to be 24 hours. It takes the same time as Earth does to spin around. And so if we want to put this into seconds, then 3,600 seconds per hour times 24 hours per day, we get 86,400 seconds. So now we'll compare it to another object going around the Earth, which would be the moon. So we'll use this equation here. We'll say radius of satellite cubed over the period of the satellite squared would be the radius of the moon's orbit cubed over the period of the moon's orbit around Earth squared. And so now I rearrange it to solve for the radius of the satellite's orbit cubed. So now I'll plug in the numbers here. The radius of the moon's orbit, which you can find on a formula sheet, 3.84 times 10 to the 8 meters, and that's all cubed, times period, which we figured out, 86,400 seconds squared, divided by 2.36 times 10 to the 6 seconds, all squared. So if I work this out, radius cubed is equal to 7.59 times 10 to the 22, and then if I take the cube root of that to both sides, I get 4.23 times 10 to the 7 meters. So that's the distance from the satellite to the center of Earth. What I asked for was the height above Earth. So then to find our distance above Earth, what we're going to do is take this number, 4.23 times 10 to the 7 meters, and then subtract the radius of Earth, 6.38 times 10 to the 6 meters, and that's equal to 3.60 times 10 to the 7 meters. Or, if we want to look at another way, it's roughly 36,000 kilometers above Earth. Alright, and now the next topic we'll look at is gravitational potential energy. And this is often one that students have some trouble with. It's a little bit different. So in the past, gravitational potential energy is referred to something like this. Potential energy is mgh. So if we pick up a rock, there's potential energy if we multiply 9.8 times the height. However, when we talk about objects in space, we'll have to use something different. And basing it on universal gravitational law, g m1 m2 over r squared, then if we take the derivative of that, we're going to get potential energy equals g m1 m2 over r. So notice it's not r squared, and notice there's a negative sign. This negative sign can be a bit confusing, but try to look at it from a different perspective. we're looking more about change than we just are about an actual number. So we have a planet and we have a satellite, and we say this satellite's a distance r. So we move that satellite, and now it's a distance r2 from the center of our planet. Well, work is change in potential energy. So that will be final potential energy minus initial potential energy. So we say negative gm1 m2 over r2 minus negative gm1 m2 over r1. If we look at the scenario we just set up with r1 being smaller than r2, if we do that, if r1 is smaller, that means this number will be bigger. And if we take the negative and the negative, they'll be positive. This will mean that our final answer will actually be positive. So if we take a satellite and we move it further away, we're doing positive work, or it gains potential energy. If we take a satellite and we move it closer to Earth, then this will be rearranged. Your answer will be negative, and that means we've lost potential energy, or we've done negative work. And so in terms of gravitational potential energy, try not to worry about the negative sign. Just kind of work through the equation and try to look at the big picture in terms of work and what's being done. Alright, so if we take a look at an example here, how much work would it require to move an 8,000 kilogram satellite from 500 kilometers above the Earth to 200 kilometers above the Earth's surface? So we're going to look at work, and work is change in potential energy, which is final potential energy minus initial potential energy. And so we write out the formulas. Now, first take a look at radius. My final radius is not 200 kilometers, it's 2 kilometers plus the radius of the Earth. So that's 6.58 times 10 to the 6. And my initial distance was 6.88 times 10 to the 6 meters. I rearranged the formula a little bit to make it a little easier to use, so I don't have to repeat terms. And if I plug in the numbers, I get negative 2.12 times 10 to the 10 joules. So this means by moving the satellite closer to the Earth, I've lost potential energy. Now the final thing that I'm going to cover with you in the screencast has to do with objects in orbit. Now there's something in your notes, and read all your notes carefully, and then in the last section regarding objects in orbit, it talks about one important formula, and this is very important to remember. It doesn't come up in formula sheets, but it's something that's going to be really useful. For an object that is in orbit, like the moon or the satellite, its kinetic energy is equal to negative 1/2 of its potential energy. And so we use this to help us find the height of a satellite. So if we know how fast the satellite goes, then we can find out its kinetic energy by saying 1/2 mv squared, and then from that I can calculate its potential energy, and then take it that much further, say negative g m1 m2 over r, and I can use that to find its height. There'll be a lot of different situations where you can use that, but it is really important that you remember this relationship here. Now for escape velocity refers to how fast something has to be traveling at when it leaves the surface of the Earth so that it has enough energy to make it up into space. So what we start off with is, if we have this object here, we're going to launch it off into space. We're just going to start, just to make it easier to look at, we're going to start with initial energy of 0. So that we say it's kinetic energy plus potential energy, relatively speaking, will be 0. And if we do that, then we're going to say 1/2 mv squared, sorry, I'll say minus negative gm1 m2 over r equals 0. I can cancel out one of these masses, and so if we rearrange there, we have g times m over r, which gives us v equals the square root of 2gm over r. So that is escape velocity for any planet or body if you know its mass and you know its radius. So if we want to do a quick example here, escape velocity for Earth is going to be equal to 2 times 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by 6.37 times 10 to the 6, and that gives us 11,200 meters per second. And that's how fast you'd have to go leaving the surface of the Earth to make it off into space.